Basic theory. Electricity can be compared to water flowing through a pipe driven by a water pump. Here we have a diagram showing a pump providing pressure to the water flowing through some piping, and a thinner segment of piping representing resistance to water flow. The parallel in electricity is the pump would be a voltage, the water current would be electron flow, and the resistance would be the natural electrical resistance that all materials have. Here we have the diagram slightly modified to reflect conventional current with electricity. We have a battery with a positive and negative terminal, and we have conventional current flowing outward from the positive terminal. And we have a small segment providing resistance to that current. Note that this is conventional current though. Electron flow actually flows from the negative terminal towards the positive terminal. But mathematically they're both equivalent, and the convention is to just have current flowing out from the positive terminal. Using the pump analogy, we can develop the Ohm's law relationship between voltage, resistance, and current. With a higher voltage, we get a higher current, and with a higher resistance, we get a lower current. So current equals voltage divided by resistance. Current is measured in amps, voltage is measured in volts, and resistance is measured in ohms. Let's have a look at a simple circuit on a breadboard. We have a red LED being powered through a 10 kilo ohm resistor. Red wire is positive and black wire is negative. We have a coin cell battery providing 3 volts. Conventional current will flow from the positive terminal through the circuit to the negative terminal, and electron flow will flow from the negative terminal through the circuit to the positive terminal. Electric current in amps is how many coulombs are passing through a wire per second, and resistance is just resistance to that current. So what is voltage? To make this connection, let's look at mass and how mass interacts with a gravitational field. Say we have a bowling ball that's some height above ground and it's falling through water, acting as resistance. Mass times gravitational pull times height equals gravitational potential energy, where m is mass, g is acceleration of gravity, and h is height. What if we didn't know how much mass the bowling ball had, but instead we were interested in how much potential energy each gram had? We could take this equation and divide both sides by m, and then we would get energy per mass is equal to gravitation times height. The units for this are joules per gram. If we look at voltage, 1 volt equals 1 joule per coulomb, where coulomb is the unit of charge. From this we can see that voltage is comparable to height times gravitational pull. So here's a bowling ball falling from 9 meters. And at 9 meters, the gravitational potential would be 88.29 joules per gram. So each gram would have 88.29 joules at 9 meters height. Here's how the gravitational potential would change as the ball falls from 9 meters. And here's gravitational potential compared to electric potential, where as the ball falls you can see how many joules each gram in the bowling ball has. This compares to an electrical circuit where at any point in the circuit there are however many volts or however many joules for every coulomb at that point. Here's a few commonly used circuit diagram symbols. We have a voltage source, which actually represents 2 pins, the positive power terminal and the negative power terminal or ground. Then we have VCC and ground, which are effectively the same thing as a voltage source, but you have the 2 terminals separated visually. We have a diode and a light-emitting diode, which are both one-way conductors pointing in the direction of the arrow. We have an ammeter and a voltmeter. The ammeter is usually used by passing current through the device, where the voltmeter usually just checks the voltage between its positive and negative terminals. Here we have a resistor and a potentiometer, where the potentiometer kind of acts like 2 variable resistors. If this potentiometer's total resistance was around 100 kiloohms and the knob was set to about the halfway point, one half of the potentiometer would be 50 kiloohms and the other half would be 50 kiloohms. And here we have a port. Ports are usually used to represent pins on devices, so some pin on an Arduino Uno might be represented using this symbol. Here's how a computer measures analog signals. A computer measures analog signals using an analog to digital converter, or ADC. The Arduino Uno uses a 10-bit resolution ADC. This means that it encodes 0 volts to 5 volts using the numbers 0 to 1023. This means that the smallest variations in voltage that the Arduino Uno can measure is 4.89 millivolts per division. So 1023 would be 5 volts, and 675 would represent 3.3 volts. Arduino as a voltmeter. Here's a simple potentiometer circuit powered by 5 volts, and the output is connected to the Arduino analog 0 pin. Like I said, potentiometers act as variable resistors, so the effect of this circuit should be able to vary a voltage from 0 to 5 volts. Here is the 3-pin potentiometer. This line represents a wire connecting the 5-volt power to one of the pins of the potentiometer, and this line represents another wire connecting ground to the other side of the potentiometer. Of course, this is the voltage source, where this technically represents 2 different pins on the Arduino. Positive pin is 5 volts, and the negative pin is the ground, or GND. Here we're going to build the circuit really quickly. We have our blue potentiometer, and we have a couple of resistors to compare to. These two are 10 kiloohms each. When working with small parts, it might be convenient to use tweezers. I usually follow the convention of red wires meaning positive power or 5 volts and black wires meaning ground. Here's our circuit with the 2 wires in the middle of the potentiometer connecting to A0, and the other one is going to connect to our oscilloscope. Right now, no wires are connected to the output of the 2 bare resistors, but we'll look at those later. We have our positive power, our potentiometer and the output pin, and our ground side. And of course, we have our voltage on the 2 bus lines. Let's connect this up to 5 volts and to A0. And just to make sure that our Arduino is telling us data that makes sense, let's use this scope to verify everything. The orange wires are the channel 1 for the oscilloscope. One of the wires has a stripe, and that's going to be the negative terminal that you want to connect to ground. Now let's write this program. Open up voltmeter and create a floating point number called rail voltage and set it to 5.00. This represents our power. In our setup, let's create a serial begin at 9600. This is your USB connection. And in loop, let's create a float voltage, and this is going to be equal to rail voltage divided by 1023 times whatever is read on our analog pin. Then let's print this out to the serial port. Here we have our scope and Arduino view. Let's go ahead and run. And open our serial plotter. So we're sitting at about 2.4 volts, and we'll wave around our potentiometer knob and the voltage varies, and we can see it on both views. The serial plotter can only see this data because we're serial printing it, where the scope is directly measuring the signal. Let's move our signal pins to the resistors just to see what the signal looks like. And it's about a flat 2.3 volts. This makes sense because those resistors aren't changing their values like the potentiometer is. And here's a view of the serial monitor with the raw data being printed to the computer. Digital signals. In this circuit, we're going to compare the behavior of a push button and a potentiometer. Both devices are going to be hooked up to analog inputs and digital inputs, and the Arduino Uno is going to visualize those as digital highs and lows using LEDs. Here's our power wire connecting 5 volts to the 10K resistor and the potentiometer. This whole segment is the 10 kiloohm resistor and the push button, with their junction connected to digital input 3 on the Arduino. Here's the potentiometer, and the output of the pot is going to be connected to the Arduino's analog input 0 and digital input 2. Arduino pin 4 is going to be used to power an indicator light for the potentiometer's voltage. If the output of the pot is above a certain threshold voltage, then the LED will light. Pin 5 will control the indicator light for the button, which will follow the same behavior. And these lines represent our ground. This time we're not going to have any extra pieces like the extra resistors that we used last time. We have our blue pot with black representing ground and red representing positive power. Our button with a resistor connecting straight to positive power and the other end to ground. A couple resistors for the LEDs. Remember that the long lead is the positive lead. Give them some ground. And here's our circuit. We have our positive power, our button circuit, our pot circuit, our pot LED, and our button LED, and our ground line. Now we just need to connect these wires to the actual Arduino. Here I'm using 3.3 volts instead of 5 volts like my circuit diagram, but our results will be the same. Here we have a bundle of wires for all of our digital pins. Pin 2 is connected to the pot's output. Pin 3 is connected to the button's output. Pin 4 is connected to the pot's LED, the green one, and pin 5 is connected to the button's LED, the red one. And we have a couple extra wires to connect to our oscilloscope. Just for neatness, I have the negative terminals for channel 1 and channel 2 connected directly to ground. And I'll connect one of the other ground pins to the Arduino ground. Ground is basically your reference point. Now let's write this program. First, create 3 integers. These are going to be the 3 Arduino pins dealing with the pot. Here we have our analog input, our digital input, and our output representing a digital signal from the pot. Let's create 2 other integers representing an input from the button and the output representing the button. Begin our serial port and set all of our inputs to input and all of our outputs to output. Here I'm just using some of Adam's fancy tricks to make quick work of this. And in our main loop, we want to read from the button and the pot and print their state and indicate their state with the LEDs. Let's serial print an analog red value from the pot, and let's print a tab symbol to create some space. Then let's print a digital signal read from the pot. Then let's read the pot as a digital signal and set the LED to that state. Print another tab to create some space. Now let's print the button's digital state and then write the button's digital state to its LED. And finish up by printing a new line. That's what println means. Connect up. Check your port to make sure you're connected. And then let's upload. The circuit's ready. Now let's run the scope and open our serial monitor. The number on the left corresponds to a raw ADC value. The middle number is the state of the potentiometer, and the rightmost value is the state of the button. You can see that the state of the potentiometer only changes after it's above a very specific voltage. Here it's around 2.2. You can also see that the button creates sharp transitions from the high voltage to the low voltage. This is what creates a digital high and a low, or binary 1 and 0. With the trigger set on our scope, we can take a closer look at the button signal, and we can actually see that sometimes when we press it, it actually flickers between a high and low state. Power. Power is a unit of measurement that describes how much energy in joules is passed per second. So a voltage supply would supply energy per second, and a resistor or LED would absorb energy per second. Power in watts equals current times voltage. All power supplies have some kinds of imperfections. One of those imperfections is an internal resistance. This is like a small value resistor that's always stuck inside of a battery. Thinking back to the circuit powering two resistors, we saw the voltage at the point between the resistors was about half of the voltage supply, since the two resistors were the same value. We can see that as we go around the circuit, some voltage is going to be absorbed by each resistor as current flows. And so, when you think of a battery, when you pull current from a battery, the more current that you pull, the more voltage is going to drop at the battery. Here's a circuit that describes the internal resistance of a battery powering some kind of load. We can see that as the load pulls current, the battery's internal resistance is going to absorb some of that voltage, so not all of the battery's voltage will reach the load. In order to examine how that voltage varies based on the current draw, let's create a circuit that draws a controlled amount of current from a battery pack. Don't worry if you don't understand the circuit, we're just using it to demonstrate how current can drop voltage on a battery supply. This is an adjustable power regulator. We have a limit resistor that sets the maximum current, and we have a potentiometer to vary the current, and then this pin goes back to the adjust pin on the voltage regulator. Then we have an LED just to show how much current is being drawn from the system. And here's a sense resistor, and we can use its voltage drop to calculate how much current is being drawn from the batteries. And these are 3 batteries in a battery pack. These 2 wires will go to one channel on our oscilloscope so that we can measure the voltage of the battery pack, and these other 2 wires will go to another channel on our scope so we can measure the voltage on the sense resistor. And here's the circuit operating. So let's power it up. Our starting pack voltage is about 4.7 volts, and with increasing current, the voltage on the pack drops. A battery's voltage doesn't just drop with increasing current draw. The battery's voltage will also drop over its use lifetime. Here's a chart showing the voltage of a copper top 9-volt battery as 3 different currents are drawn from it. You can see that if you only draw 50 milliamps, you're going to see slightly more than 8.5 service hours. At 100 milliamps, you're going to see about 3.25 service hours, and at 250 milliamps, you're going to see only 1 hour of service. We can see from our examples of batteries having varying voltages over their use and lifetime that we need some way to create a stable voltage level so that we can power our circuits. This is where regulators come in. Voltage regulators generally come in 2 flavors, linear and switching. Linear regulators absorb excess voltage to create a constant output voltage, and switching comes in 3 variants: buck, which is able to lower voltages, boost, which is able to raise voltage, and buck boost, which is able to do either one. Here is a common linear regulator called an LM7805. It's a 3-terminal device capable of supplying up to 1.5 amps. It will output a steady 5 volts as long as the input voltage is anywhere between 7 and 25 volts. Here's an Arduino Uno, and here is the power regulator. Here's the Arduino schematic, and the red section is the power regulator portion. When we zoom into it, we can see that the part number is NCP1117. If we look that up, we can find that it's a 1 amp low dropout voltage regulator. Low dropout just means that it can take in input voltages that are lower and closer to its output voltage. This one has about a 1 volt dropout voltage, which means that it can take inputs as low as 6 volts and still supply a steady 5 volt output. Here's a buck switching regulator that's based around the LM2596 chip. You can see the regulator as a whole is more complex than the linear regulators that I showed, but the benefit of switching regulators is they can be more versatile and can even have higher efficiencies than linear regulators. The benefit of linear regulators is that they're simpler. Here's a 7805 regulator regulating a varying input. The yellow line represents a varying input voltage, and the blue line represents the regulated output. The red LED is unregulated power, and the green LED is regulated power. You can see that the output stays a steady 5 volts just until the input voltage reaches a lower limit, and then the output voltage can't be sustained. Here's the Arduino Uno regulating power. We can see that it has pretty much the same behavior, except the main difference between this and the 7805 is the dropout voltage, or the lowest allowable input voltage. And here's the buck switching regulator operating. Now let's talk about current and current capacity. A power source like a battery will have a certain current capacity, which is current times number of hours. If a battery can supply 1 amp for 1 hour, that would be 1 amp hour. And if it can supply half an amp for 2 hours, that would still be 1 amp hour. So say for example we have a high altitude balloon that needs power for a 3-hour flight, and we have a hypothetical payload that draws about 100 milliamps. We would need a battery that has at least 300 milliamp hours. Now let's look at some batteries and see how they compare to each other. Here's a nickel metal hydride rechargeable 9-volt battery, and it has a rated capacity of 175 milliamp hours. Here's a zinc manganese dioxide battery, and this one looks like it has 300 milliamp hour capacity, but only at 5 milliamp of current draw. If we compare these two to our hypothetical balloon scenario, neither of these would be a good choice. Here's a battery with the same chemical makeup, but it looks like it's a little bit heavier, so it might have an extra cell inside. This one's capacity is around 400 milliamp hours at 100 milliamps of discharge. Compare this to our balloon scenario, this one would be a decent fit. Here's a 9-volt lithium cell. We can see a couple of differences with this battery chemistry. We have a 1 amp maximum discharge rate, and we have a capacity of around 750 milliamp hours at 100 milliamps discharge. We can also see that the voltage over the battery's lifetime stays much more constant than the previous chemistries. Thanks for watching.